Yeah, you commit to the input. That will be the first thing. That's what we sent.
Yeah.
Yeah.
At the start.
Yeah, it's that. Then at the end, you have to case the exactly.
Wait,
Then,
like the commitment will be sent together with the GKR approval. So.
yeah, exactly. But it has to have been put into the transfer. Everything that is in the proof must have been put into the transfer or something. Okay, so let's continue with FRI. We should know how to fold now, right?
Yeah.
Right?
Yeah. So you have your polynomial.
Yes, so you have your original polynomial.
Yeah.
Yes. You interpolated to get that.
To get the
Or
polynomial.
or if it was given to you already in coefficient form, then that's fine, right? Then the next thing is that you need to now evaluate that polynomial over
And
the
roots of unity.
yes of the
Based on
size
the
of the
blow
code
up.
word. Yes, based on the blow up
Blow
factor.
factor.
So the blow up factor times the message length will tell you how long the code word needs to be. That should be a power of 2. Then you're now gonna find like the nth root of unity. Then you use that to evaluate. Then you get your code.
That generator.
You use Aquox.
Okay.
Yes.
Okay.
So that FFT field. So f dot get roots of unity. Then you pass n. Yeah.
We were implementing FFT
N.
Yeah.
ourselves.
Yeah.
We are still using the algorithm.
You use the Aquox package for your omega, but then the FFT algorithm is like a different algorithm. Yeah, exactly. So we have the first polynomial, right? F of x. Then we blow it up into a code word by evaluating it at all the roots of unity at that point, right? So then the next thing is that we need to get the f2 polynomial by folding, okay? So once we have gotten the Merkle root hash for this, the prover is going to send that Merkle root hash to the verifier, and the verifier is going to respond with an R, okay? So let's say the verifier responded with R. So what we're going to do is that we're going to split this polynomial, this f polynomial, into 2 different parts. That's the even part and then the odd part. Then we'll factorize out x from the odd part so that both of them are like even functions. Then we'll factorize out x squared so that we'll flatten it out so that we reduce the degree. And then we now merge both sides with r to get the next polynomial. That will be f2 of x, right? And then we also extend that based on the blow factor. So since the degree is broken down into half, then that means the code word also broken into half. And that way you have reduced the problem. Then you continue this process until you get to the point where or an agreed length between you and the verifier. Let's assume they agreed on constant. So once it's constant, you don't need to send a Merkle root hash for this, right? The verifier can just look at it and know whether it is of the right degree. This is not too much work. Now that this is as verified, then as long as you can prove that you folded everything correctly, then the verifier will now be convinced that the top guy is of the correct degree bound. Does it make sense?
The proof is the what's it called? The Merkle roots.
All the Merkle roots. And then the degree of this is the commitment, sorry. The commitment, not the proof. Yes. Is all the Merkle root hashes and then the actual value for the last guy. That's the commitment. That's the commitment.
All of the Merkle roots and then the last.
And then this last, yeah. So the commitment will be like, there's a lot of commitments, right? It will like Merkle 1, Merkle root hash 1, Merkle root hash 2, Merkle root hash 3, and then finally you have like a constant. So this is your commitment. This is just you binding yourself to like the polynomials.
But if the prover and verifier now agree to get to the constant,
yes,
you can just stop at where the Merkle root distance stop at.
But then you need to send the last, whatever the last thing is, you are sending it in the open. Do you get? Like you're not committing to that last thing.
So So let's say that it's
Stops.
just M4.
M4. Yes.
Yeah.
So
It's just saying M1, M2, M3, and M4.
and M4. But now M4 not the Merkle root hash, the actual values,
Okay, actual value.
the leaves of M4. Do you get? Because whatever you're sending is now something that the verifier is supposed to be able to interpolate and then check the degree.
Okay.
Make sense? So this commitment. Now we need to figure out how do we relate two layers together. That's the goal now. How do we relate two layers together? If we can relate two layers, then we'll be able to prove that the folding was done correctly. Okay? Yeah, that's the consistency check. Once we have a formula that relates two layers, then the verifier can just like check for the consistency of the two different layers.
Is that where the squaring from?
Yeah, so you're going to like link the roots of unity. The roots of unity at the top, the one at the bottom is just the square of the ones at the top. But then when you square it, there's an overlap between 2, 2, 2. So that's what reduces. So there's some relationship between the two layers. So that's what we want to figure out. So let's start. Let's assume we are starting at f1, right? f1 of x is equal to some polynomial, right? There's another way to write f1 of x. You can write f1 of x as g of x squared plus x times h of x squared. Does this make sense? So, and then how do we now get the next layer? Right? The next layer, that's f2 of x, is what? Is g of x, okay, plus r times h. This is how we get the polynomial for the next layer. So we get, from the first one, we get out g of x, and we get out h of x. And for the second one, we take those two, and then we fold them based on r. Let's just do an example to show that this is actually correct. So what example? Just give me a like 3 plus 2x plus 3x squared plus 4x cubed, right? This is our f1 of x polynomial. Now we need to get g of x and h of x. What would g of x be? Yes, so that would be 3 plus 3x. Remember, it's g of x. Yes, it's even. But I'm already factorizing out x squared. Let me not jump. Does it make sense? Or should I do it step by step? Step by step, okay. So, the first thing we need to do is we need to move all the even powers to one side, move all the odd powers to another side, right? So this is 3 plus 3x squared, right? Then plus 2x plus 4x cubed, okay? These are all the even powers, and these are all the odd powers. Cool? Then once we have this, we factorize our x. Or we have factorize our x first. Yes. So that will be 3 plus 3x squared plus x into 2 plus 4x squared. This is still our f1 of x. Now we're going to call this part g of x squared. Okay? And we're going to call this part h of x squared. So this is going to turn into f1 of x is equal to g of x squared plus x times h of x squared. Okay? Now if this is g of x squared, what is g of x? So we said that g of x squared is equal to 3 plus 3x squared, right? So that means there is a g of x that we are evaluating at x squared. So what is this g of x? Exactly. So we just like divide all the powers of 2, all the powers by 2, right? To remove out the x squared. So that's 3 plus what? That's our g of x. Then what of h of x squared? That's going to be 2 plus 4x squared, right? So what's going to be our h of x? Cool. So this is our g of x, and this is our h of x. Now, it's the g of x and h of x that we need to build the next polynomial, the f2 polynomial. So this f2 polynomial is basically g of x plus r times h of x.
Yeah.
Oh? Yeah. Kind of. No, I was getting confused with that. So the way I'm explaining it now is like, when you have gotten your g of x and your h of x, the verifier will now give you r, right? And then you use that r to merge the both of them. And that's how you get the polynomial for the next round. Does that make sense? So let's assume that r is what? R is 2, okay? So what's our f2 of x then? What's g of x? 3 plus 3x, right? Then plus 2 times what? 2 plus 4x. So that's what? 3 plus 3x plus. So that's does this make sense? So our f1 of x is what? Someone writes it down.
F1 of x is
3 plus
3x
plus
3x 3 plus 2x plus 3x plus 4x.
and then when we folded it with r equals 2, we got f2 of x, right? Which is 7 plus 11x. Makes sense?
Yeah.
Now what we would like is a formula that relates these two polynomials. As given some values here, you can figure out what this polynomial would evaluate to. That's how we connect two layers. And once we can connect two layers, we can do our consistency check. But does the folding make sense?
Yeah.
Okay. Now let's figure out the formula. So I started by saying that f1 of x can be expressed as what? G of x squared plus x times h of x squared. Then f2 of x is now what? G of x plus r times h of x. There's a relationship. Okay? There's a relationship between the two. So I guess the first step is now figuring out, like, how can we get g of x in terms of just f1 of x? That's the first problem. I want to express g of x in terms of f1 of x. Okay? What does this represent? This represents all the terms in f1 of x that have even powers. Right? So, is there a way to evaluate f1 of x or do some kind of manipulation in f1 of x that when we're done, we'll only be left with the terms there that have even powers?
Get rid of the
How do you get rid of even powers? With maths.
with powers.
That's like all the terms that have even powers. We
Oh.
want to get rid of them in maths. So like this is f of x, right? This is what I want to get rid of. I want to get rid of I want to get rid of the terms that have odd powers. Because this is supposed to be, so I'm supposed to get rid of 2x should disappear, and then 4x cubed should disappear. So what I should be left with is 3 plus 3x squared.
Subtract it.
Subtract what?
Subtract what's going to get rid.
So what it's saying now is that I should do like 3 plus 2x, right? Plus 3x squared plus 4x cubed minus the things I want to get rid of,
Yeah.
which is 2x and what,
4x.
right? But then
You
How-
want me to
how do you do this mathematically? Like assuming that I cannot see the polynomial itself.
oh,
Do you get? Like the polynomial is just a black box to me. Just think of it as f of x. How can I achieve this?
okay,
Set
I,
x to 0.
So I think I should evaluate f at 0.
it will affect the,
If I evaluate f at 0, then all the terms will go except for the constant, right?
so, you can generalize, but I still hold on to this subtraction, but by generalizing, I think the general formula for even is n plus 1.
You know formula for what?
Even number. Sorry, odd number is n plus 1.
Okay.
Sorry, 2n plus 1.
Okay. So what do we do with that?
So, if we can subtract both sides, but you will make sure that you are subtracting 2n plus 1 for all n.
So what does that materialize into?
You've successfully subtracted all.
No, I mean like concretely, what should I do?
Okay, I should tell you what to write.
Yeah.
Let's say you have some polynomial f of x,
Okay.
and you want to get rid of the even power,
The odd powers
the
first.
odd power
Yeah.
of the polynomial. You will then say, f of x minus summation
Summation of what?
of summation of x raised to power 2n plus 1 for n starting from 1 to, or I starting from 1 to,
Yeah, but what are the coefficients?
I don't know how to get the coefficients.
Yeah,
Like,
but
for
you know,
me to get the coefficient, for me to know the coefficient, I must know the polynomial, because polynomial does not have the,
because what you're suggesting now is like you're just subtracting the even powers of x, the odd powers of x, right?
yeah,
But then if like the first odd term you get is like x, just x, right? But then in the polynomial it was 5x. That would just result in 4x. But you didn't successfully get rid of the entire x.
I get
You
your
get what I'm
point,
saying, right?
I get your point. I understand. I'm supposed to put maybe an plus 1 or a.
But how you get a?
That is the question. I need to know the polynomial before I
You
do
don't
that.
need to.
I
But
don't need to.
let me now explain. So what you do is that what happens if you evaluate the polynomial as minus x? Are you getting it? So let's say I evaluate this f1, right, as minus x. So anywhere there's x, I'm going to replace it with minus x, right? So this is going to be 3 plus 2 times what? Plus 3 times minus x raised to the power of what? Plus 4 times minus x raised to the power of what? So this is going to be 3 minus 2x, right? Then plus, minus x squared is x squared, right? So that's still plus 3x squared. Then minus 4x cubed. What have we been able to do?
The odd terms are not negative.
All the odd terms now have negative, are now negative, right? So this means that we can add this to the original, okay?
And they will cancel out.
So they will cancel out, but something else will still happen, right? So what we're trying to,
Doubled. The even term will be doubled.
exactly. So we're doing f of, right? Does it make sense?
Yeah.
So that's going to be what? 3 plus 2x plus 3x squared plus 4x cubed, then plus 3 minus 2x plus 3x squared minus 4x cubed. Make sense? So what's going to happen? All the odd terms will cancel out. but the even terms will double, right? So that's going to be 6 plus what? Now, how do we get back just the even terms?
By those
We divide by 2. So
Divide
this, no, if you factorize to 2 will still be there. You want to get rid of it
by
completely.
two. Divide.
Do you get?
okay.
So it's like f1 of x plus f1 of minus x divided by 2. This will give you just the even terms. Make sense?
This work for all cases.
Yes. I don't like
As long as you
yes, a univariate polynomial in this case. So you just like, because the reason why is like a negative sign raised to the power of any odd
Odd number.
is always going to remain negative. But it's raised to the power of an even, regardless of, it's going to become positive. So this is like a clean way to kind of like make the two distinct. Make sense? So now this is going to give us all the even terms of that f1 of x, right? And what were the even terms called?
Yeah, like,
G of x squared. Right? If you look at this, we're dealing with this, right? And what did we call this side? G of x squared. And what is this side? Only the even terms. Does that make sense? So that entire expression that I've written can be dropped in here, and the equation will still be exactly the same. Does that make sense? Now, let's say we want to get this h of x squared. How do we do this now? We'll add what?
F of x.
Uh-huh.
Sorry, you subtract f of x from negative x from f of x.
Okay. Yes. So now for h of x squared, right? What are we trying to get rid of? We're trying to get rid of the even. So it's the opposite of the other one, right? And we already know that f of minus x, we put a negative sign on all the odd. But then if we wanted to now put a negative sign on all the evens, what do? We multiply by minus 1 or subtract. Do you get? So to flip the sign of everybody. Does that make sense? So so if we do like, what we're trying to do now is f of 1 minus f of. So if this was originally going to give us all the a negative sign in front of all the odd terms, because of this sign here, it's not going to give us a negative sign in front of all the even terms. Okay? And then when we do the subtraction, we're basically going to just be left with all the odd terms. Okay? But we're not done. We still need to divide. We need to divide by something. Okay, so what's f1 of x? That's 3 plus 2x plus 3x squared plus 4x cubed. Then what is f1 of minus x? No, minus f1 of minus x.
Minus 3 minus
minus 3 plus 2
plus minus 3x squared plus 4x cubed.
So you can say that this one and this one are just flipped, like the signs are just flipped. That's the only difference between the two of them. Okay? Now, we're basically getting rid of the even terms, right? So what are we going to be left with? This one will cancel. This one will cancel. So our left is what? 2x plus 4x cubed plus what? 2x plus 4x cubed. Does this make sense? Then what's the sum? Right? Make sense? But now, was that our h of x squared? This is our h of x squared. Divided by 2x. Does it make sense? what we have done so far is that we just said f1 of x. Give me all the terms that have like odd powers. Okay? But then that's basically the same thing as just moving all the odd. That's basically what it's giving us right now. Is giving us that part there. Right? And what did we do to that part? We removed x. Okay? So we need to divide not just by 2, because of the doubling, but also divide by x also to get rid of that x. Yes, exactly. So h of x squared is equal to what? f1 of x minus f1 of minus x divided by. Make sense? So now we have an alternative way to write g of x squared and h of x squared. Does that make sense?
Why we care about doing it like this? Because of implementation.
Because we want to link the two layers so that we can do our consistency check.
For the implementation.
Theory too. We need to know how to relate this layer with this other layer. Because if not, we will not be able to verify that the prover folded each layer correctly. Like we need to show that you said you had this, right? You said you had this code word, then I gave you R. Then you were supposed to do something with that R and the code word that you have, which is to break it and then fold it, right? I need a way to know that you did that thing correctly. If not, the protocol is not complete. Because the prover could have literally used maybe another R instead of the R that you gave them, or use another code word instead of the code word that they said that they had. So if you can't verify that they did everything correctly, then they can just fabricate that, oh, this is my constant at the end. Take. That means that everything is correct. But then it could have been dishonest from the get-go. Maybe we started with a degree 20 polynomial, and then it folded into a degree 4 polynomial. It just went from 20 to 4. You need a way to prove, so you need some kind of algebraic relationship between the first code word and the second code word based on R. And that's what we're trying to like figure out. Okay? So, and our g of x squared is what?
3.
Right? So that means that we can rewrite our f1. Or we can rewrite our f2. Both should work, right? So our f2, you know, our f2 of x was basically equal to like g of what?
X plus R equals X.
Right? So, and we have a formula for g of x squared and h of x squared. Right? So what this means is that our f2 of x is going to be, so we're now doing like g of root x plus r times h of root x. Does this make sense?
Root x or root x squared.
No.
How do you root one of two equation?
It's a g of x. See, let me write our f1 too. There's a way to do it without your roots though. Right? This f1 of x, does it make sense? Now f2 of x is using g of x after you have already like factorized out like the x squared, not factorized, but like, you get what I mean? Does f1 of x make sense?
Yeah.
What of f2 of x? F2 of x also makes sense. So if you have a formula that expresses g in terms of x squared, then g of x is basically like, how do I put it? Yes, it's basically a square root, but I'm trying to explain it in an easier way.
Can we use a concrete?
I thought it's supposed to write
Can we use a
One
concrete?
over two.
Use a concrete example.
I think you should not just put it directly into like squares.
I think what you're trying to do is you're trying to
When you are
reduce.
trying to separate it into
You're
like
trying to reduce the polynomial.
Multiple people are talking.
You're trying to
Wait,
reduce.
Listen.
I'm saying that instead of writing it like duplicating it in the sense of 2x, that's contradictory, right? But what you should just do is to express
Oh, it's
put
contradictory.
h of x. If you are separating the h of x squared in quotes, when
I'll
you
call
write 1x minus 1 plus, in that x you now put square root of x. Like in that
And yeah, that's the goal. That's the goal.
Huh?
Okay, yeah, I get what you're saying. I get what you're saying.
What if?
That's accurate.
Have you gotten rid of the X project? Samuel,
To come back.
I've gotten rid of it.
Temporarily.
Gotten rid of the X.
So
There's a way to get rid of root x by squaring though, but yeah.
the F2 I do where it says f of x equals to g of x plus r plus h of x. The one you just played.
Okay.
So why are we having root x again? If f of f1 of x is g of x squared, and we are saying f2 of x is g of x, it's supposed to be so f2 of x can also be g of root x squared, because if the root cancel the square to still give you x. So why
Yeah,
is
yeah.
it now?
It was my so I'll say I made a mistake, like writing it that way. Okay. So these two g's are the same, right?
Yeah,
It's just that this time, the first time they evaluated at x squared.
yeah,
Why for the further one they evaluated at x,
yeah.
right? Now we have a formula for the x squared version of g, right? So h of x squared is this, right? And g of x squared is that. Now what is h of x? No.
F1 of
square root of
Do you get?
The square root of
If I wanted to, I have an expression for g of x squared,
yes.
but I need an expression for g of x to be able to know how to get f2 of x. So if the expression for h of x squared is this, then what's going to be the expression for h of x?
Just to do square root on both sides.
Exactly.
And then there's not the h of root
So
x
h of x is f1 of what? Does this make sense?
Yes.
So I think it's like
Sorry. Makes sense?
Wait, so if we are coming from h x squared and you want to go to x, like it's looking like h of root x squared will now be h of x. Then like I'm putting the root x squared in the brackets because that's how x squared can turn to x.
So it's like, remember at the top too, we had yes, so see all these relations.
Exactly. So this one's now it was like multiplying the powers by half, which is like square rooting.
The same thing. Like x, if x raised to the power of 1, if you multiply by half, that's x raised to the power of 1 over 2. X raised to the power of 1 over 2 is exactly the same thing as.
Root x.
So the way you wrote h of x was by just writing h of x, right? Then you now square rooted all the powers of x. Or you like multiplied all the powers of x by half, right? We had h of x squared equals to something. Then you just wrote h of x equals to all the powers of x divided by 2. That's exactly the same thing. we have h of x squared here, then we'll just write h of x. But then all the powers of x, which in this case is 1, 1, 1, multiplied by half. And then that's how you have like square root of x here. Does this make sense? And it works, right? Because if you evaluate this at x squared, what's going to happen? It will be f1 of square root of x squared. What's square root of x squared? X, which is what we have there. And minus square root of x is. Does it make sense? Cool. Now, the question is, what are these two values in relation to this value? Okay, sorry, wait. So our f2 of x is now what? Remember our f2 of x was g, right? Plus r, right? But now we have an expression for g of x and h of x. So f2 of x is basically what? f1 cool, right? Right?
Why is it 2 on one side and 2 roots?
You know, remember that when we divided by both 2 and x, because we doubled, but then there was also the x that we factorized out from h squared. So like f, where is it? Yeah, this side now. Right? That's just going to give you all the terms with odd powers of x. Okay? Which is basically all this here. Okay? But our goal is not this. Our goal is the h of x squared. So how do we get h of x squared? We factorized out x. So that's why we divide by x. Okay? So that's how we have the formula for h of x squared and g of x squared. Okay, so this is an x. You know, right? I'm coming. This is an expression of f2 in terms of f1. Are we seeing it now? Now there's a link between the f1 layer and the f2 layer. Maybe. There's a link between the f1 layer and the f2 layer. This means that now we can check if the folding was done correctly. Does that make sense? But yeah, just listen. Let me know when you're done. Okay. Any questions so far? Is it clear for everyone? Okay. Now I was asking a question. What is the relationship between this x here and this f1 of root x?
That means if you square root the x in f1 of x,
Mm-hmm.
you will get the x in f2 of x.
Is it with square root or with square? Right?
If you square the x in f2 of x, you get the x in f1 of x.
You said if you square the what?
If you square the x in f2 of x,
In f2.
yes, of
Uh-huh.
x, you get the x in f1 of x.
No. You get the x in the next layer. This is related to roots of unity. Okay?
the next layer.
Yes.
If you
That's why.
square,
But if you square root,
Yeah.
then you get the one at the top.
you square root,
That's
you
not
get the
the
one.
way we did
No,
it. That's not the way
No.
we did the root
Relax.
ability.
Relax. 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 Okay.
He said square root, though, not square.
Yes. Relax. Just relax. Eh? Just calm. So what? Let's say top layer, fourth root of unity, right?
Yeah.
So that'll be what? 1 minus I. Is it 1 minus I? Yeah, 1.
1 minus 1, I minus I.
1 minus I. Is it? Minus.
1 minus 1, I minus I.
No. It's still fine. They're all correct. It's just permutations.
That's supposed to be iron.
Yeah, it is I. Now, what is the second root of unity? 1 and minus 1, right? Is it making sense?
Yeah.
So now, this one is the square of this and this, right? If I wanted to get the two things at the top, what do I do to the one?
Square.
Are you getting it? Huh?
Don't get two things at the top, please.
Which top?
So, wait. If I want to get, 1 came from what? Minus 1 and 1, right? So if I know this now, and I want to know this and this, what do I do?
Square root down.
Do you get?
Yeah.
Does it make sense?
Yes.
So that's basically what I'm saying here, that if you know the x at f2 layer, then to get the equivalent x that you need to evaluate the f1 layer at, you just square root that x, and then maybe put a, but that's like both the pairs, right? Positive and negative sign. That's why this one is the positive one, and this one is the negative one. Does that make sense? So if I want to evaluate f2 at 1, right? That's this one here. Okay? What am I going to do? I'm going to evaluate f1 at what? 1 plus f1 at what?
Minus 1.
Is that making sense? Are you sure? So there's an easier way to write this that gets rid of all the square roots. Should we try that? Let's try that. So let's now look at things from the perspective of, you know, So this is another way to write it. You can say f2 of x squared now, not f2 of x, is going to be equal to f1 of x plus f1 of plus r times they're exactly the same thing. It's just the view, but they're exactly the same thing. So the way you, if you are looking at the roots of unity as, the way you get the root of unity for the next layer is by squaring all the roots of unity at the top. Then this might be easier to reason about.
So we're not going from top. We're not going like this. We're going down.
You are going down. Does it make sense? It's still the same thing. Because at the end of the day, to know what is here, you need to square root.
Square.
There's no running away from that.
Huh?
There's no escaping that.
Well, in the actual protocol, what will happen is that you'll be given this x and minus x. So you will know instantly what this thing is talking about. So you're doing more of like a squaring. But these two are exactly the same. But the point I'm trying to drive at is that, so we'll do an example, like a proper code word, then we'll fold it, and then we'll show that the relationship holds, so that everything is clear. But the point now is that anything in the F2 polynomial can be gotten by the values in the F1 polynomial. Okay? And this should start showing you how consistency checks might be possible. So to make consistency check possible, the prover, the verifier wants to know that you folded this correctly, right? Remember, folding is going to take two different things and merge them into one. So we're going to take a value here, and we're going to take another value here, and all of them will merge into one. So let's call this one x, and let's call this one minus x, right? Like the 1 and minus 1. Then it's going to give you a new result that is going to be here, and this result is going to be x squared, right? Because remember this, like minus 1 minus I, right? And then this one is now 1 and minus 1. If you look at this 2, it's kind of like you just squared. If you square 1 and you square minus 1, you're going to get 1, right? So this layer can be seen as the x squared for the layer above. And if you square I and you square minus I and you square I, you're going to get minus 1, okay? So all the prover needs to do to verify consistency is that it's going to say you have given him the Merkle roots of all this, the different layers, right? So that means they can ask you to open this at any point and generate like a Merkle proof. So what it's going to say is that I'm going to query you at x, okay? Tell me the value that is at x. And you're not just telling the value, you're proving the value because you've already committed to a Merkle tree, right? So you're telling him the value that is at x, you're also giving him a Merkle authentication proof, or part. So once it gives you this value, you also tell him to give you the pair of x, that's minus x. So it's also going to give you this value too. And then it's going to give you what the answer is supposed to be. So the prover will give x, the value at x, so I'll just call it xv, the value at minus x, and the value at x squared. Okay? Now once you have these three, you can check whether everything is correct. What do? You take the value at x and the value at minus x, and then you plug it here. And you remember the arrow that you sent to the prover, you plug that here. Once you plug everything, you yourself will be able to independently compute what the value at x squared is supposed to be. Okay? Once you now get this value independently, you now compare it with the value that the prover gave you. You get? That way, you are able to verify that it did the folding correctly. Basically, what you are doing is that the prover is going to do the folding for a lot of values. Then you are going to do the folding for just one value. But because the prover did not know which x and minus x pair you are going to ask for, the prover could not cheat. It had to be honest all through. Does that make sense? Let's do an example so that it's not as confusing. We're going to do one layer folding for values that when you square them you get the same thing at the bottom. So I'm not using the roots of unity because I don't want us to be doing evaluation in I and minus I in a complex space. So let's say this is our f1 of x. Right? Now what's our f2 of x? What did we get again? You say?
We got 7 plus 11x.
7 plus 11x. Now let's build the code word for those two layers. Okay? Now we're assuming that when we multiply the message length by the block factor it was 4. Okay? Just an assumption. Now let's use just values that have pairs. That's all. So let's use 3 and minus 3. Then let's say 2 and minus 2. Okay? That'll be our interpolating set. So the thing about roots of unity is that when I do this now and I shrink to the next layer, the pairing will no longer exist. That's the problem with just like using. So this only works for one layer. But roots of unity, if you shrink it down, the structure, that half will be the negation of the other half, will still exist. And then you can keep on doing that infinitely. But this one now is just going to be like one step. So when I square this and this, I'm going to get 9, right? So 2 values there will give you the same value, right? And then when I square 2 and minus 2, I'm going to get 4. So we have the interpolating set of both. Cool? Now let's fill the values in. You see? Now I just picked 2 arbitrary points. That's 3 and 2. And then I also put the negation, just so that we can have this roots of unity like structure. So what's the evaluation of F1 at 3? Okay. 3 plus 2 times 3, right? Plus 3 times 9. Oh my. Does anybody have a cow?
The last one is 108.
Which one?
108. 108 plus 27, 6.
144. Okay, what of 2? What of minus 3? So that'll be 3 minus 6 plus minus, say 108, sorry. Minus 72. I'm going to do for minus 2. That's 3 minus 4 plus 12 minus 8 times 4. That's what? 32. Is that? Minus 21. Okay? So this is the first code word. Hopefully it's correct. But this is the first code word. Now let's get the code word for F2, assuming he has done the folding already. So what's F7 plus 11 divided by 9? That's 99 plus 7, right? That's 116.
So the 9 and 4.
Yeah.
Is it evaluating as root of infinity? Root of
So to get the next domain, you square all the top guys.
for the top guys, how do you get them?
I just picked arbitrary.
Okay, just pick.
Something that looks like root of unity, but it's not actually the root of unity. I could have used like 1 minus I minus 1 and. But then the disadvantage of this is like it only works for one layer. But like if you see now, 9 and 4 don't have this positive, negative structure. But if I had used the root of unity, I'll have gotten 1 and minus 1. So wherever it starts in the root of unity, you can keep squaring it down until you get to a constant value. But then this one is just for one layer, but that's sufficient because that's enough for me to show that the consistency trick.
Just 3 and 2, you put them on the
Yeah, I picked them
You
arbitrary.
also pick
Yeah, exactly. I just created a structure that had positive and negative pairing for every single number, so that when you square them, two things will give you exactly the same thing. If you add 8, I'll pick 3 values, right? And then their negations. Sorry, 4 values and then their negations. But it only work for 8 to 4. When you get 4 now, you're not going to have 4 things that have that structure anymore. But if you use roots of unity, you will have that structure. But this one is enough for like... What's the last one? Sorry. What's 7? 106. Then what's of 4?
These values now, how did you get them?
Yeah, evaluating, the goal is like F1, you evaluate it over the roots of unity. Then F2, you also evaluate over its own roots of unity. So this is how we're getting the code words. Okay? We folded with R equals 2, right? Right? Can't remember. Okay. So now we have the code words. Right?
Is it the folding from yesterday?
Mm-hmm. We did another example today. Does this make sense so far? Does it make sense? So all we did was took the polynomial, evaluated over the domain. Then we folded to get this new polynomial, right? And then we evaluated our new polynomial over the domain also. Make sense? Now what we want to do is, I want to show that there's a link between this and this based on the formula that we use, that we just created. Okay? So let's say I wanted to evaluate F2 at 9. Okay? I wanted to get F2 at 9. One of them is wrong. What is that? Minus 17 is 4. Do we need to cross check? Because if it's wrong, the consistency check will not work. Probably just those are the wrong values. Because that's basically like the prover doing something malicious and committing to an invalid code word. But yeah, let's just start. If it's wrong, then we know that something is wrong up.
Are they supposed to equate each other?
Which one? These two? This one and this one? Somewhat the values? No, not necessarily. They don't have to. But it's going to. They should relate to each other based on this formula. That F2 should be equal to something using F1. Okay? We're good? Did you confirm the rest? Okay. So now F2 of 9, right? That's our goal. Our goal is F2 of 9. What was the formula again? F2 of x squared, right? Is equal to what? F1 of x plus F1 of what? Divided by 2, right? Plus R times F1 of x minus F1 of minus x divided by, okay? Now if we're evaluating F2 of 9, so we're trying to figure out a way to get F2 of 9 only using values from F1. Now, want to do F1 of x. 9 was representing what here? X squared. Okay? So what will x be? 3. Does it make sense? Make sense? Because this F2 of 9 is similar to writing like F2 of like 3 squared. And then that instantly shows that x is 3. So we're going to do F1 of what? 3 plus what? F1 of divided by 2 plus R was what? 2. F1 of what? F1 of divided by, which is divided by 6.
Is it 3 or 2?
X is 3. And it's 2x.
I thought you were doing odds and ends.
What do you mean?
Like,
I'm just using this formula here.
yeah, okay, you're going to do this for each x, or
Yeah, I'm doing
I
it
feel
for
like this
9.
side is supposed to be for the odd.
Okay, what would that change?
Like with the 3 knots, with the F1 of 3 on this side, not the F1 of 2.
No. So see, this f2 of x squared, right? It just distributes x all the way.
So it's just for that.
Yes, so it's still the same x. Okay. So this is what 2 times 3, right? That's 6. Make sense? Now what is f1 of 3? What is f1 of minus 3? I'm supposed to add them, right? Divided by 2. Plus 2 times 144 minus 84, right? Cool. What is 144 minus 84? 60. Divided by 2, which is 30, right? Then plus 144 plus 84. 228.
That's 83.
Remember there's a 2 here.
Yeah, that's 66.
So we can exactly. We can cancel out this thing. Right? So just 228 over 3. What's 228 over 3?
76.
What's the summation? And what's the actual value? But we got it 2 different ways. Are you saying? We got this one entirely from just using values above. Does it make sense?
So is this still following that FFT method and stuff? Because I see the coding, but the workings and stuff with these 2x and that is the denominator.
Yeah, this. When did you join the class?
So,
we created a function, right? That relates 2 layers together.
okay.
Yes. So that function is this.
Is this one?
So this F2 then is just F1. It's like in GKR where W1 or
Yes,
WI
yes,
divided by WI plus 1. It's exactly the same thing.
Makes sense.
Okay. So does that make sense? So you can see that formula actually does relate the 2 layers. Should we do for F4? So let's do for F2 of 4. F2 of 4 is going to be what? The same thing as F2 of what? 2 to the 2, right? Which is basically F1 of what? 2 plus F1 of what? Divided by plus R, which was 2, times what? F1 of minus divided by 2 times 2, right? So we just cancel from here so that it's easier. Okay. Now what's F1 of 2? That's 51 and minus 21. So that's what? 51 plus minus 21 divided by 2, right? Then plus 51 minus 21 divided by 2. What's 51 minus 21? Then what is 51 plus 21? 72?
Over 2.
What's that?
That is 36.
Then what's 15 plus 36?
31.
And you can see that that's 51 also. Is it making sense? So what the consistency check is now this. The prover has already computed these 2 vectors. That's it. In the commitment phase, it was just so it's like it computes the first vector, then it Merkle hashes it, and then it sends the Merkle root. Then the verifier is going to give him R. That R is what it's going to use to fold to get this new one. Then it's going to evaluate that also, right? Merkle commits, send, get a new R, R2, use that one to fold, and they continue this process until they get to the bottom. Okay? So now the prover is basically doing it for every single value. Now, to check that the folding was done correctly, all the prover, or all the verifier is going to do is they're going to say, okay, I want you to show me that you folded, let's say based on 3. Right? So it's just going to be looking at 3. So the prover is not supposed to give him what? The value at 3, the value at minus 3, and the value in the next layer at 3 square. Okay? So it's supposed to give him what? F1 of what? Of 3. F1 of what? Minus 3. And then F2 of 9. So now once he has given these values with the Merkle authentication part, so that the verifier knows that it's not lying about those values, then it's now going to take this F1 of 3 and F1 of minus 3 and plug it into this formula. And at the end of the day, it's going to get a value. Now this value is supposed to be equal to this F2 of 9. So it's just going to do a comparison. Is it equal? If it's equal, then that folding must have been done correctly. Unless, let's say, it did everything incorrectly except for that.
Particular part.
Exactly. So what happens is that the program makes multiple queries like this. So they say, oh, evaluate at 3. Oh, now evaluate at 4. It's not going to do everything, but because the program would not know beforehand where it's going to pick, it is so hard to try and like make things not work. Yes. Does it make sense? Yeah. Yeah, sure.
No, down.
Oh, down. Okay. Good?
So, my question.
More?
I want to write.
Good?
Yeah.
Yeah.
My question is for the Merkle action to,
Yeah.
to get the root. Is there a library?
You write it yourself. If you are implementing, you write it yourself.
Write everything.
Preferably, yes. You should then you should be happy. You should like like this is a chance. Hey, write it in Rust. Write it in Rust. It's not that crazy.
Can we verify a F1 at minus 3?
Yes, then you give the opposite. Yes. You're just giving the pairs, the opposite pairs. So there'll be an algorithm to figure out like what should I give. Yes. It's based on the root of unity. If you just negate the root of unity, you get that. So if you give it minus 3 and you negate that, so you get 3. So you just know that okay, I'm supposed to give that 3. Does it make sense?
So,
Yeah. No start system.
so now we have done for 2 layers, that's F of 1 and F of 2.
Good question, yes.
Yeah. Can we like move a layer below so we can get like, you know, once we get like 3 this thing, we can now like
Let me show you what the process will look like
yeah.
if you had more than one layer.
Yeah.
So you have a code word. This is the first one, right? Then you had another one, which was half. Then you have another one, which was half of that. And then you have another one, which was a half of this again. And let's say you get the final one, which is like the constant. Now you want to do consistency check for every single layer. Now you, the verifier, you remember all the R's that you used, right? Remember that I sent you R1 when we're going from this layer to this layer. I sent you R2 when we're going from this layer to this layer. I sent you R3 for this, and I sent you R4 for this, okay? So I used to do the consistency check for every single one of them. So what I'm going to do is I'm going to pick a query point at the top, just one query point. Let's say this is a query point, and let's call this A, right? Now you have to send me the opening of A, okay? The opening of minus A, and the opening of A square, okay? Now once you have done that, I'll do my consistency check. But then, this A square is not like my query on this layer. It is my A. Do you get? So at the end of the day, it's now has to send you exactly. And then it's still a square technically. It's not a square, I mean it's still a square of whatever is here, right? You're just going down. Don't get
It's keeping somehow, like, before when we are folding,
yes.
we are reducing the power by 2.
Eight.
Like from A4, like before, the normal polynomial, as we are going down, it's reducing by 2.
Yes.
But now, if you're getting a square, A4, so it's also increasing
So
by
remember this, right? Let's start from 1. If you find square root of this, that's what? Find square root of this. Is it I minus I?
Yeah.
Then we asked ChatGPT to help us with these other ones, right? This one is still 1 minus 1. This one is still I minus I. Then let's just call this one A. No, let's call this M. Oh, wow. Makes sense? So, let's say you had the original code word that had 1, 2, 3, 4, 5, 6, 7, 8. 8 values. Okay? So when you encode it, you're going to encode it with, let's say 1, I, M, N, minus 1, minus I, minus M,
That's a random order.
minus N. Yeah, I'm just doing like all the positives first and all the negatives. Does that make sense? Now, the next layer, you are going to use the next root of unity, which is what? 1 minus 1, I minus I. Make sense? Then the next layer, you're going to use the next root of unity, which is what? 1 and minus 1. Then the final layer, which is the constant, you're going to use the last one, which is just what? Now, let's assume you picked this as your A. So this is A, right? Then this is going to be what? I square is what?
Minus 1.
Minus 1. So that means your A square is what? Okay? Then you pick the negative, right? Which is what? Then now, A raised to the power of 4.
Is that the negative?
Yeah.
Yes.
Wait, is that negative?
Minus I raised power.
No, it's minus 1. It's minus 1.
Yeah, sorry. This is what minus I, right?
Yeah.
So it's supposed to be this, right?
1,
Make sense? Now, what would these two go down to? Is it not 1?
yeah.
It's 1, right?
Yeah.
Now, this one, depending on how you look at it, what is A? A is still what? Do you get? So this technically is just what? Is it making sense?
Yeah.
Or what you could also do is that you could rename this, right, to be equal to B. So A square is now B. And then this now becomes what? B square. But it's still the same thing. Then you now pick the minus what? A raised to the power of 4, right? And then you get this one, which is going to be what? A raised to the power of 8. And remember, the root of unity is such that any value in that root of unity raised to the power of n is going to be equal to 1. And in our case, n is what? 8. 1, 2, 3, 4, 5, 6, 7, 8. That's why a raised to the power of 8 is 1. Does it make sense? So, do you understand how consistency check works now? Even for more than one.
So meaning that the verifier is just asking for point is going to be asking for point at the root of unity.
Yes, at the top one. So just a, for example. Then it has to open minus a and then a square. But then it also has to open minus a square and then a raised to the power of 4. Then it's going to open minus a raised to the power of 4 and then a raised to the power of what? Then it's going to open what? right? And then a raised to the power of 16. So this now is assuming that we started with like the 16th
16.
root of unity. Okay? So basically it's just opening different Merkle trees. So the reply to this query is just Merkle authentication, Merkle proofs, basically. That's what the value is and the authentication part. Then it's doing that for every single value here. That's FRI. That's FRI. So the only thing now is like it's not as bad as GKR now.
Yeah.
See? It's not as
Bad as GKR.
Yeah, very.
It's not as bad as GKR. So you just do this query a couple times. So the query the number of times you do the query depends on the security analysis. So like what the size of the field that you're using, or what's the blob factor that you use. So the bigger your blob factor, the less queries you need to make.
I think FRI GKR has so many moving parts.
Yes.
It's not very technical.
Yes.
FRI doesn't have a lot of moving parts,
Yes.
but it's very technical.
Especially
It's
if
not
you
very
start
bad.
going. Yeah. In terms of like this is just you guys are at like layer 2.5 of FRI. It's deeper than stack 101. Then you guys have touched code words a bit, and then so yeah, I want to talk about this thing now. So how would you let's look at implementation a bit, right? How would you so there's a naive way to do this. It was talking about that so you have a polynomial in coefficient form. What you could do is that you could represent it in an array. What is it? That's how you guys do it right now, I think. Right? So if I just represent this, I want to show you how you can fold potentially in coefficient form. So what do you do? F1 of x is what? 3, right?
That's for question.
Univariate coefficient form. Yes.
Well, in our implementation, what are we going to be working with?
You start with univariate coefficient form. Then, yeah, you're now going to the code word. Yeah. Yeah, this is normal. Yeah, this is the polynomial. Then we're going to use FFT to convert it into a code word. FFT converts a polynomial from coefficient form to evaluation form. So we're going to use that to do our. Normally, you're supposed to like interpolate this and then evaluate. But yeah, I'm coming. So when you're done with this, right, you're not going to use FFTs. Actually, you're going to do with Solomon, one way or the other. So you now get a bigger code word. Okay? Now, you could now get the next polynomial. The way you get the next polynomial is by. So now I'm trying to get it from this one now.
You said like we're not going to use the normal Lagrange.
Ideally, yes. They both do the same thing, but one is just slower. Yes. You use FFTs to convert this evaluation form. So the goal.
We are supposed to implement the FFT ourselves.
The goal is to get 711, right? For the next one. How would you do this? You get the even terms in one array.
There's 3 and 3.
Then you get the odd terms in another array. What was our R? 2. So we multiply this one by 2. And then we add everything together. Okay? So that'll be 3, 3 plus
8.
then if we sum this, what is that?
7, 11.
And that's exactly
Okay.
the folded. So it's very easy to fold when you're in coefficient form.
So we don't need with Solomon then.
No, you still now have to blow this up. You know, every time you get your polynomial, you're now going to evaluate your polynomial at the roots of unity. So we know we got this one first and we got this one. Then we now evaluated this to get this, which is with Solomon. And we evaluated this to get this, which is with Solomon. You get? So this folding is just folding your univariate polynomials. So once we have gotten the folded version, you now run with Solomon. So when you run with Solomon on this, you're not going to get something of half t. Does it make sense?
Yeah,
But-
but what if the verifier asks for a root of unity in the initial array?
This is the commitment phase.
But if we
It's not yet the query phase.
if we interpolate and evaluate, we still get
You still get the same thing. It's just speed. Yeah. It's not what we're in the commitment phase now. So you had a polynomial that you wanted to commit to, expressed in evaluation from equation from univariate. Alright? So you take the initial polynomial first, run with Solomon to get the code word. Now you want to get the next polynomial they are going to run with Solomon on. So what you just do is that you just split those two polynomials in two halves, multiply the second half by r, and then merge the two of them element-wise. So you get a new coefficient form univariate. Then you run with Solomon on that to get the next code word. Then you fold again, the same way, split in two, multiply by r, merge with Solomon. Then you continue until you get to constant, and you're done. Does it make sense?
Yeah, kind of.
But the yeah.
This first, yeah, that 3, 2, 3, 4. That's our original polynomial.
Yes, that you're trying to commit to.
Now trying to commit to.
Yes. Makes sense?
You know, you've been saying it. The one we are folding is not the polynomial, or is it the code word?
It's the code word you're folding.
So we're not folding.
No, you're
this.
folding both. It's like they're equal. You know, the code word is just the polynomial evaluated at more points.
Oh, okay.
So, and if you do Lagrange on both sides, you're going to get the same f of x. So they are exactly equal. It's just this one adds more fidelity, which is like adding more distance to the code word. Make sense?
Yeah, but which one are we
Which one are we folding?
The one you're folding in this example I've given you now
Yeah.
is the polynomial.
But
Then when you fold it, you now use with Solomon to get the equivalent code word.
Oh. Wow, I thought getting the with Solomon was first, then you now fold.
So there are multiple ways to do it. And yet, you get, so you have your polynomial, you get with Solomon, yes. Then you fold to get a new polynomial. They are both the same. Yeah, but when you're, no, you remember yesterday we were talking about like, I think it was the case that was like, it's in evaluation form. So the folding doesn't really work. That's like the splitting it into two. Yeah, so this is the correct way to do that split thing. It's on the, yes, on the equation form. You do it on the equation form. Then once you get the results, you now do with Solomon again. Then you do the same thing here. You split, that'll be 7, 11, then r, then you merge it, so that'll be one value. So that's a constant. So that's like the constant. Does it make sense?
Continuously, you said you do Solomon just the first.
So that's what I will now ask you guys now. So you have seen a way to do the commitment, right? Where you are doing with Solomon on every layer.
sorry, what is with Solomon?
With Solomon is you take a polynomial and then you evaluate it at a lot of points.
What is the difference between that and FF?
FFT allows you to do with Solomon fast.
Sorry, but it's at lot of points. My evaluation, but lot of points.
Oh, FFT now allows you to do that same evaluation but at the root of unity.
Allows you to do it fast using the roots of unity.
Oh, using the root of unity. With Solomon does not use like normal.
It doesn't care about roots of unity. With Solomon is just that your polynomial is a degree D polynomial, right? That's a degree 3. So that means that your polynomial can be expressed with just 4 points. With Solomon is like, I want to add redundancy to this polynomial. So I want to evaluate at more than just 4 points based on the blow-up factor. So maybe blow-up factor is 2 or 8. If the blow-up factor is 2, then with Solomon is saying that I want to evaluate at 8 different points. It doesn't say anything about what those points should be. But if you want to make that evaluation fast, you use the roots of unity.
That's very difficult.
Yes. But FRI specifically cares about the roots of unity also. Because of the way we link those two. So if you are doing with Solomon alone, outside the context of FRI, if you are okay being slow, then you can use something other than the roots of unity. But if you want it to be fast, you use the roots of unity or anything that has roots of unity like structure. Yes, where it's like it's a collapsing set. That's like if you square everything or if you do some operation on everything, there are two things there that will give you one thing there. And then when you get the resulting thing, that thing also has that same property. So, yeah.
So how does interpolating and evaluating do the same thing?
Interpolating and evaluating is the same thing. It's like you interpolate the coefficient form, right? No, you already have it. If you already have it, okay, wait. You only interpolate if you have the evaluations.
Which we already have the
This is the coefficient.
yeah.
So that means you can just evaluate straight away at all the roots of unity. Like,
just evaluate straight away.
yeah.
This is like our y values now.
No, that means you are looking at evaluation form. This coefficient form. This is what? This is const. This is x, x squared, and x cubed. So this polynomial is something as 3 plus 2x plus 3x squared plus 4x cubed, which is what we have here. This is the coefficients of the polynomial. So that means that's already been interpolated. Does it make sense? So to get your Ritz-Solomon encoding, you want to evaluate this polynomial at more points than the domain.
So that's why. So meaning if we are using FFT, we are just using either the one that blows it up, like either FFT or IFFT, the one that just.
The one that converts from coefficient form to evaluation form.
This is so and what when we're doing univariate, we are taking this and we are doing 0, 1, 2, 3, 4 to
0, 1, 2. Yeah, no, you're not taking this to do that. You are taking the evaluations. So let's say this was 2x plus 1, right? I can evaluate at 0 to give me what? 1. I can evaluate at 1 to give me 3. This is the one that you put 0, 1. And then you do your Lagrange interpolation. But there's another way to write this. You can write it as 1, 2. This is the constant, and this is the coefficient of x. So this is the coefficient form representation of the polynomial. That's what is here. You get? So you now fold this, you get a new one, and then you now. So now, I was like, what's the current process? The current process is that.
Sorry, before you go to the current process. Now, since you say that stuff is already the coefficient, which means it has already been interpolated, right? And which means if we want to get our code words, we just have to evaluate, right? And the other way around to also get the code word is to make use of FFT, right? And you say FFT is faster. Since we are not interpolating and evaluating, how is FFT faster since we are just evaluating straight? Is it that FFT is faster? Because I was thinking FFT is faster because we are interpolating and evaluating. But since we are just evaluating, is FFT still faster?
So, if you want to evaluate a polynomial, now you're evaluating it at a lot of points. And the polynomial itself already has like n terms in it. So every evaluation is going to do n multiplications. Because we have to do constant plus something times x plus something times x squared plus something times x cubed. So you're going to do n of those, right? So every single evaluation is O of n time. Right? But now you're going to be doing a lot of evaluations, not just one. So it's like, let's say you're doing m evaluations. So that means your entire running time is O of mn, where m is much greater than or greater than n. right? So this is the running time for regular evaluation. That's the read Solomon using regular evaluation. Now, if you're using FFT will do everything for you.
Read Solomon. So read Solomon is just evaluating at random values.
Exactly.
And blowing up the polynomial.
Yeah.
Encode.
So that's
That-
the error correcting.
Yeah, adding distance, exactly.
Oh. Add names to full
Exactly. When we understood what read Solomon was, we were like, why did they call it this? But obviously, it makes sense because of the people that did it. But there are a lot of terms that you see that are so, they sound so crazy. Like, damn, this concept is going to be hard. But then once you now understand, you're not like, what is this?
If I just evaluate the polynomial at random plenty point, that's read Solomon.
It depends. No, so read Solomon, there's a block factor.
Uh,
There was the message length. Then there's the code word length. So read Solomon is basically like a way to take a message of size k and then blow it up into a code word of size n. But then n is equal to k times, I think it's d, but I don't know whether that's the right blow up factor. I don't know if I should call it d. I don't think it's d.
I want to know what the
No, d will probably be the grade, but let me call it b. But this is wrong. There's an actual symbol. I've just forgotten.
blow
Yeah,
factor.
the blow factor.
Wait, sorry. Which one is blow factor? Which one is key?
K is the message length.
K is the message.
Remember that everything we were talking about error correcting code is like you're trying to send a message over a channel to somebody else, but that message you need to add redundancy to it. So that message length is k.
So K is like D.
K is like d plus 1 in polynomials. Yes.
So how does the blow factor come in? Is it like it's sent or
No, it's
or you get it from the polynomial?
no. It depends on how much error you want to tolerate.
Alright.
So if you don't want to, you want to tolerate more error, you make the blow factor more. Exactly.
So if you have something like, if you have something like our K is 5
Yes.
and our blow factor is 2,
Yes.
that's 10.
Yeah, I'm going to send code words of length 10.
But
So-
we need it to be power of 2.
Yes. So you need to make sure the power 2 before you can use like FFT.
So how do we make sure
You can pad.
compared
You can pad with just zeros until the power 2.
zeros?
You can pad with zeros until the power 2. Make sense? Then once you pad with zeros, so like you have your polynomial here, and then you now have some like extra stuff.
No, I'm just but that will not be the evaluation of the.
No, like you don't pad with zeros. You evaluate the polynomial at, how do I put it? At more points. So read Solomon itself, right, doesn't really care about the power of 2 thing. This power of 2 thing is coming from FFT. FFT first. FRI is using FFT or FFT like. So that power of 2 thing is the only way that FFT will be efficient. So FFT like is like I can evaluate a whatever thing you give me at a lot of points really fast. But my requirement is that the points I want to evaluate at needs to be a power of 2. So that is now placing like restrictions on the structure of your problem. So if it's not a power of 2, you need to just pad it into a power of 2.
Okay. So we see the
Yeah, you go to the
next.
next power of 2.
So how is FFT related to its unit?
Okay,
Yeah, FFT. How is it related to
I'm coming. I'll get to that. I want to just finish. I want to ask you guys a question first, but let me write it here. Like, because now that would mean that okay, I'll now start going into FFT a bit. But wait. Now, what we have so far is we have a polynomial, right? And then we perform what? Read Solomon. Okay? To get the code word, right? Then we fold. And then we perform what? Read Solomon again. To get the smaller code word. Then we fold again. And then we perform read Solomon to get. The question now is there a way to still get this without having to do read Solomon on every layer. Because read Solomon is O of n log n. That's the running time for read Solomon. And O of n log n. Obviously, the n is getting smaller as you go down, but it's still. So the question is like, how can we prevent the use of read Solomon, which is using FFTs, on every layer?
Apply this formula we got.
Exactly. So that formula, those formulas that we got, that shows you how to express F2 in terms of F1. The prover can also just use that to evaluate all. Do you understand? So that's like you don't even need to do the folding anymore. Does that make sense? So you just start with the first polynomial, f1 of x, right? You do the RD to get your code word. So let's say you had like 4 values. Then you don't care about this side anymore. So what you could just do is that you just create a new one. But to get the value here, you use the formula with this value and this value, right? This will be your f1 of x, and this will be your f1 of minus x. Then you put it into that formula, and then you get your f2 of whatever, and then you just write that here. Does that make sense?
It's very familiar.
Okay. So, we have a formula. Where's that formula again?
F2 of X.
Yes. This one here. This formula can tell you what the value of f2 will be, right? Given 2 values of f1. So when we wanted to get this 106, we use 144 and minus 84. So this means that you can get every value here by just using all the values here, right? You just take them 2, 2. So you
have
take,
to know which two to pick.
yes, you will know based on you know true code, like the ordering, then the square and everything.
Okay.
The roots of unity.
Alright.
Not really. It's like, just say you know the first root of unity here, right? You know the domain for this, so that's 9. What's square root of 9? That's 3. What's the negative of 3? Minus 3. So you just take those 2, and then you do the same thing for this, right? So once you take those 2, you just plug it into this formula, and then you get out the correct value, and then you just write that in here. And then you take the other 2, plug it into the formula, get out the correct value, and then just write that here. So you're going to do that for everything. So then you're running in like O of n time, as opposed to O of n log n to get each other folding.
So that means we won't need to solve one again.
Exactly. That's what I was saying yesterday. You only need to do with Solomon for the top just once, but you can get the rest just using this. Make sense?
Yeah, so does the verifier care about order?
No? The verifier doesn't see all of this.
So you actually write 3 minus 3.
Yes, yes. That's for faster. That will make your code faster because of your cache locality is there. So everything is next to one another. So you're just taking in groups of 2s. So you take 2, 2, 2, 2, then calculate. Rather than taking one from here, then going all the way to the other side, take the other one. If the half was like bigger than the cache, then when you take this one, it will load the first half in. And when you want to take the other one, it will throw away everything and then load the next one in, which is just like expensive. That cache, this thing is really expensive. So putting it side by side is possible. And then there's a way to even put it side by side that the next layer would also be side by side.
I think it's automatic.
So I don't think it will be directly automatic.
Like, you put 3 minus 3 goes to 9.
Let's do it for this one. Alright. Okay, I think this is a proof that it's automatic, right?
Yeah.
Yeah, so if you arrange it in this order, then it works. But there's an ordering. It's not just like automatic. It is automatic because of, like, you could have done 1 and minus 1, right? Then you could have done m and minus m. Technically, it still fits that the negative pairs are together. But then that particular arrangement would not have led to something that was also arranged, right? Because we did 1 and minus 1, then you did m and minus m, you get 1 and you get I.
So,
So I was like, there are multiple arrangements you can do for this, right? You can do 1 minus 1, right?
yeah.
Then you can do m minus m, and let's say I minus I, and n minus n, right? Now when you merge these two together, you're going to get what? And when you merge these two, you're going to get what? When you merge these two, you're going to get, and this one you're going to get. Now this one is not in that nice structure.
Yeah.
But then if you had done it the way it is down there, 1 and minus I, then m and minus m, and n and minus n, if you merge these two, you're going to get 1, right? Minus 1, I, minus I. Now this one too is also in that structure. So you just take 2, 2 again. And then the next one too should be in that structure. And you take 2, 2 again. So depending on how you arrange the top, every other thing could either be arranged or not arranged. Does it make sense? So yeah, so you just do FFTs or read Solomon at the top, get the code word, and then you just use that formula to fill up the other ones. Does it make sense? Any questions? Any questions?
For this, the initial, like the F1, is it going to be the,
Creation form.
no, is it going to be the polynomial, the code word?
No, F1, you always start with a polynomial that you want to commit to. Then you now convert that polynomial into a code word. So once you have gotten the first code word, you can get all the other code words.
Okay, it is a code word that we are performing like this relationship on.
To get the next code word. Then you perform on the next one to get the next one, perform on the next one to get the next one, so you get to that your desired point, which might be like the constant.
I'm confused because when I asked, you said that it could be either
Either
the polynomial or the code word.
2.
So,
Yes. So
now you just said that you can put it
we have described 2 ways of getting all the code words. The first way is that you start with the polynomial, right? Then you do the read Solomon, right? Then you fold the polynomial by splitting it into 2 halves, right? Then multiplying the second half by r, right? And then adding to get a new polynomial. It's now your f2. Then you also use read Solomon again to fold, right? And then you do the same thing again, right? Then plus r times this to get this. Then you could, it's not that long, but this one makes sense, right? Problem with this is that you're doing with Solomon every layer, which is like, if you do it without FFT, that's n square. If you do FFT, that's n log n. Okay? But now, instead of doing it this way, there's now a second method, right? So now you're folding the code words directly. This one you're folding the polynomials, and then you're using it together. So this other one is like, you do f1 of x, right? Then you get your code word. You do the read Solomon once. Then once you're done with this, you now use that formula, that f2, to now get all the values here. And then you use the same thing, and then you just, so you just do rs just once. Make sense? So FFT. Why roots of unity for FFT, right?
So this FRI
F what?
this FRI
Yeah.
is quantum resistance.
Plausibly quantum resistant.
What about GKR?
GKR is not a cryptographic. So all information theoretic protocols are they're not like how do I put it? There's no assumption there. Information theoretic is that regardless of the power of your adversary, it can never break it. So it's now when you try and bring those protocols to real life, that's when you now bring in cryptography. So like remember IOP, we're saying that they were sending oracles. But then when you come to the real life, that oracle now is a commitment and an opening, right? And then those commitments and openings now have their own trade-offs. Like KZG now is using ellipticals, but then the information theoretic protocol itself doesn't care how you instantiate it. It's just saying that this is the protocol, and this protocol is like secure because there's no assumption. When you now bring it to real life, you're not going to infuse certain assumptions in that this is secure, assuming that this cannot be broken. But this one is just like information theoretic. So GKR is like an information theoretic protocol. But when you're not implementing it, you guys are now using like okay, Martinia, KZG, and those are bringing in assumption. So you can minimize the assumption by using another, let's say another PCS instead of just. Make sense? Let's say, so FFT, roots of unity. Why it is important. You know the goal is that you have a polynomial f of x, right? And you want to evaluate this polynomial at n points, right? That's how you get the code word. The reason why you want to use FFT for this is because of I'm coming. Yeah, it's because of you don't need to kind of like it's related to that even function thing that we're talking about, where if f of x is even, right, you don't need to evaluate both the positive and the negative, because of if f of x is even, then f of x is going to be equal to what? And when you're using roots of unity, you always have like something like a, b, c, right? Then minus a, minus b, minus c, right? So if you, let's say you wanted to evaluate an even function at all these points, you only need to evaluate at the first three. You don't need to evaluate at the last three. Because of whatever answer you get here is the same answer that you're going to technically get here. And whatever answer you get here is the same answer you're going to technically get here. Whatever answer you get here is the same thing you're going to technically get here. So you're just going to evaluate at half. Then FFT is basically an algorithm that takes advantage of this. So FFT will also split the polynomial into even and odd powers. So you know regular polynomials are not necessarily like even polynomials by default, right? So what you should do that is not get something like this also. Now these two are even, so you can save work there, right? So rather than going to these two and then, so right now when you want to evaluate this polynomial at a, b, c, minus a, minus b, minus c, for this g of x and h of x, it's only going to evaluate it at a, b, c, and a, b, c. Because of, once it knows the evaluations at a, b, c, it instantly knows the evaluations at, because it has made both of them even functions. Does it make sense?
Yeah.
So it's not like, if it was an even function, it would be the fastest, right? Because we just do half and then you're done. But this one now, because of it's not even by default, it's not going to be as fast as that, but it's going to be faster than when you did like the full evaluation.
Yeah, I understand. So normally, so it's more like if we do our normal evaluation,
Yeah.
We will do only ABC. I won't do minus A minus B minus C.
Yes.
But with FFT,
Wait.
we want to do it still separate. We can still separate them. Then
Wait. Sorry. The first one you're talking about was with FFT or without FFT?
without FFT,
Is that without FFT, what happens?
we can do ABC and just put the remaining values since we know that they will be positive ABC.
You mean like if f is an even function?
Yes, if F, yes.
Yeah, if f is an even function, yeah.
No, is it even now? I'm talking about we're doing it normally on roots of
FRI.
unity.
Uh-huh.
I'm applying it to the whole right now. So we're doing it on roots of unity. So if we evaluate A, B, and C, we don't need to evaluate minus A, minus B, and minus C.
If it's an even function.
Yeah. Okay. So even if we're doing it on FRI and it's not an even function, we have to evaluate everything.
That's the point of using roots of unity.
Okay.
In the sense that it gives you that pairing. So normally I'm supposed to do 1, 2, 3, 4, 5, 6 evaluations. But then if I start to have an idea of like the structure of my polynomial, then I can start reducing some evaluations. So if I know that my interpolating set is the roots of unity, if the interpolating set was not the roots of unity, you always have to do every single thing. If the interpolating set is the roots of unity, and my function is an even function, then obviously I can.
Okay.
But then what is really cool about the roots of unity is that that's not like there's a repeated structure. So let's say I wanted to evaluate an even function at all these values here. Okay? Oh, the way I wrote this is not nice, but let's see the other one. I think we did it in another place. I'll send this. Okay, yeah. It's still the same thing. I wanted something nicer, something that had like all the positives at one side and then all the negatives on the other side. But let's just write it out. So let's say A, B, C, D, right? Then minus A, minus B, minus C, minus D. Now, if we're using FFTs, right, we only need to, let's say even functions and the relative evaluation, we only need to evaluate this side, right? But once we evaluate this side, that side is kind of like given. But then there's another cool thing in the sense that this side too can also be broken into half.
This side. For roots of unity.
The square, yes. If you look at it really well, where is this other thing? All the values here, all the values here are here.
Yeah.
All the values here and all the values here.
Oh, that is not the block.
The extras.
Yes.
What do you mean by block?
The drum that scene.
Kind of, yeah. But see now, it means that if I want to now evaluate this half, right?
Yeah.
Because I know that if I evaluate this half, I instantly know the evaluation of this other half,
Yeah.
right? Now, this is my new problem. Evaluate this half. But evaluating this half too also has that positive negative structure. In the sense that for evaluating this half, I also only need to just evaluate this two.
So if you evaluate those two, how do they tie am?
Yeah?
If you evaluate only those two, how do you not get tie am?
Wait, I don't get. I'm coming. If you evaluate only those, okay, we have learned.